And this is on.
Yes.
Okay.
Yeah, please.
Okay. Hi, my name is Brett. I'm with Devera, and today I would like to share the work I did with Nick, who is also a graduate student in our group, and Marlon, who is a postdoc in our group. So the title of my talk is Bath Engineering Magnetic Orders in Quantum Spin Chains. So I'll go through the outline of my talk. So first, I'd like to discuss why we want to study dissipated spin models. And then I'd like to talk about something that we all know, which is the thermalization to a Gibbs state. And then I'll introduce this model that Nick developed, which is called the effective Hamiltonian method, that allows us to study a quantum system that is strongly coupled to its environment. And I'll use this method to apply to various types of spin models, and then I'll conclude. Okay, so why do we want to first study spin models? Well, we just heard from the previous talk that it offers a versatile platform for study of different quantum materials with exotic properties. And also spins are utilized in quantum devices. But in actual experimental setups, these systems are inevitably coupled to environment. So there's often a system environment coupling, sometimes incontrollable. And so we would like to study the dissipative spin systems. And there's already a lot of work being done in dissipative systems, but most of them are almost purely numerical, and they also assumes weak system bath couplings. And also they are very specific to what kind of system you have or what kind of bath you have. So the aim of this project was to provide a sort of general analytical approach that can tackle a variety of different dissipative scenarios to various different spin systems that goes beyond the usual perturbative regime. So we are also interested where the spin system are strongly coupled to its environment. So that's the motivation. Now I'd like to talk about something that we are all familiar with, which is that if we have a macroscopic system that is coupled to its thermal environment, if you wait long enough, the probability distribution of the system being in the energy states are given by the Gibbs distribution, like that. But for a quantum system, microscopic or nanoscale system, this might not be correct. That is, if you have the density matrix of your system, and then if you let it evolve for a very long time, the form of that density matrix will not be characterized by the system, purely system Hamiltonian, because there's going to be a strong interaction between the system and the bath. So this formula here is only true for weak system bath couplings. So, but we are interested also in the strong coupling regime. So how do we do that? So Nick developed this method called the effective Hamiltonian method. So the goal of this method is to imprint strong system bath coupling effects to the new system, and that is now weakly coupled to the bath. So then we can use the usual weak coupling techniques to a strong coupling problem. So I'll first begin with how this method works. So first, we begin with a generic open quantum system described in panel A. So the system Hamiltonian is presumably strongly coupled to the bath. And then what we do is we redefine the boundaries of the system and the environment. So we extract some mode out of the bath, which I'll explain what this RC means, but what it is it's going to enlarge the size of the system. And this is now going to be weakly coupled to the residual bath. So you redefine the boundary of your system and the bath. So your system is now this, is now going to be weakly coupled to the residual bath. And then what we do is we do this rotational frame such that we're going to develop additional coupling between the system and the residual bath, but this will allow us to do allows us to weaken the bond between the system and the RC. And then what we do is at the end, we want to recover the original size of the Hilbert space by truncating to the lowest mode of this RC. So all that is at the end, we start with this Hamiltonian, the total Hamiltonian, and then we end with this effective system Hamiltonian that is weakly coupled to the residual bath. And then we can use recoupling techniques to this Hamiltonian. So I'll now go through each step in more detail. So this is panel A. So one begins with a very generic open quantum system. So you have a system part, the bath part, and the interaction part. System can be here taken arbitrary. The bath is described by collection of harmonic oscillators. And then the interaction between the system and the bath is described by this Hamiltonian here, where S is the system operator that acts only on the system Hilbert space, and it couples to the bath displacement modes. So this is the harmonic displacement operator with coupling strength Tk. So this is a way to write a generic open quantum system. And the bath is usually characterized by this thing called spectral density function, which is by definition given by this is sort of like a weighted density of states where each weight is given by the coupling strength squared. And for this talk, I'm going to focus on this special type of spectral function called the Brownian spectral function, which is simply a function that has a peak and it has a characteristic mean omega and width gamma. And these two parameters will come later as it will be important in the later step of this mapping. Okay, now we extract a mode out of this bath, and so we're redefining the boundary between our system and environment. So we have extracted some harmonic mode out of the original bath, and your system now only couples to that single mode, and that mode couples with the residual bath. So here you can see that the notation has changed for the bath harmonic oscillator operator. So from CK to now BK, so these now describe the residual bath. And this transformation is unitary, so it is exact. And you basically define this reaction for the modes described by A dagger, and A, and it's just the linear combinations of the original bath modes. And the important thing of this mapping is that it's going to change the way the spectral function looks like. So from the original spectral function that looks like this, it's going to change it to a linear spectral function where the parameter that controlled the width of this original spectral function now becomes a prefactor of this new spectral function. And so if we assume that this spectral function has a very narrow width, then this RC mode, this RC transformation allows us to capture a weak system bath coupling, because now this gamma, if it's taken small, it describes weak coupling between the system and the bath. And also this lambda, which is the characteristic interaction energy scale between your system and the bath, and the characteristic bath frequency. So these are the energies for the reaction coordinate and how strongly your system coupled to that reaction coordinate. They can be obtained from the original spectral function in this way. Okay, now what we do is we do a rotation of this. So it is yet again another unitary transform, where the unitary transform is given by this form here. And all it does is it's going to shift the RC operators by this factor here. It's essentially a polar ion transform. And then what it does here, so this tilde now is the system Hamiltonian rotated by this unitary. It's not going to do anything to the RC mode, but it introduces this new term, which is the given by, so it generates new system interaction given by this term here, and it also shifts the A dagger and A by this amount here. So that's so from the previous Hamiltonian, once you do this polar transform, you get this Hamiltonian. And then so far everything was exact. You're just doing consecutive unitary transforms, and then we do an approximation, and that approximation is that the RC mode that we extracted, which is essentially a harmonic oscillator, so it has a equally spaced energy level. We're going to restrict ourselves to the ground state of that harmonic oscillator, and this approximation is valid if you assume that the largest energy scale of your system is this characteristic frequency big omega. So if it's larger than the typical energy scale of the system delta, then you can safely assume that you're restricted into subspace. And so we're basically going to truncate to the ground state of the RC mode given by this projector. And what that does, it's going to get rid of A dagger A and also A dagger plus A. And so from the previous slide, if you get rid of those, we essentially are left with this Hamiltonian here. And now this looks the same as the starting Hamiltonian, that your new system Hamiltonian is given by this, where it introduced new bath-induced interaction between the system degrees of freedom, which is now weakly coupled to the residual bath. And now we can use the weak system techniques, for instance, that in the long time limit, the steady state density matrix for the system is accurately captured by this effective system Hamiltonian. And from this, we can compute a variety of physical observables, thermal averages using this density matrix. So that's the mapping. Now we're going to apply this mapping to spin systems. So I'm going to talk about three systems. So here's the legends of what these things mean. So every one of these dots are spins, and then these the light blue shades are bosonic bath. And then whenever two spins or many spins are in the same bath, they're coupled globally to that same bath. And the coupling that I'm going to take is always going to be sigma x interaction. So the interaction between the spin and the bath is going to be sigma x. And I'm going to talk about these three models. First is the antiferromagnetic Heisenberg model that is fully coupled to the giant bosonic bath. And with this effective Hamiltonian machinery, I'll show that this will lead to antiferromagnetic to ferromagnetic ordering change. And I'm also going to discuss a transverse field Ising model that is coupled to in this semi-local bath. So this is the pairwise coupling where two spins are coupled to their bath. And we'll show that it will become from antiferromagnet to extended Neal ordering. And also finally, I'll also show this Ising model, but that is fully connected. So all of the spins are connected to the rest of the spins. And from this model, we'll show a quantum phase transition from the antiferromagnetic Ising interaction to a ferromagnetic Ising interaction. So these are the three things that I'll show. So first is, so this is the first example. So the Hamiltonian is simply given by this. It's the Heisenberg model. And the coupling to the global bath is given by sum of all the sigma x operators. And after this effective Hamiltonian machinery, there are three things that happens. One is that this will suppress the spin splittings for the individual spins by exponential amount. And also there's going to be a mixing of the the interaction in different directions. So although for the X, it does not change anything, for Y and Z interaction, it's gonna mix them in this way. And finally, the most important part is this thing here, which is the bath-induced ferromagnetic interaction given by this form here. And this is going to be all-to-all interaction. So it's not just nearest neighbor, because we're going to square this, you're going to generate long-range interaction as well from this thing. So the plot here shows the structure factor for this system, which is, for here, it's simply just sum of all the XX correlations that is appropriately normalized. And here I'm showing the sigma X structure factor, and here I'm showing sigma Z structure factor. And what happens is as we tune the strength from 0 to some finite value, so as we increase the strength of interaction with the system and the bath, what happens is it becomes from an antiferromagnetic state to a ferromagnetic state. And if you want to see how they look like in real space, each of these correlations, it goes from this checkerboard style to ferromagnet. And the structure factors in other direction, they all just die out because we're applying a strong, essentially applying a strong magnetic field in the X direction. So although they begin in an antiferromagnetic state, all the long range order dies out. And this is captured by what limiting value each of these takes, and they will essentially take 1 over n being the length of your system. And what that means is that the only surviving correlations are the autocorrelators that lives in the diagonal. So here we can see what this method can give us. The suppression of spin splittings, the admixing of the spin-spin interaction, and generation of bath-induced ferromagnetic interactions. This is now the second model, the transverse field Ising model, with this pairwise coupling. The universal feature that we always see is that the spins in the direction that is not to the direction of the spin that are coupled to the bath is going to be suppressed. So we again see this suppression of sigma Z. And also spins that are coupled to the same bath, they will generate ferromagnetic interaction. But the spins that are in the boundary will continue to be having an antiferromagnetic interaction. So this picture shows from weak coupling to strong coupling, what happens is essentially the wave vector that describes this antiferromagnetic order, it doubles. And in the middle, we see this complete suppression of long-range correlation. And this is simply due to the fact that if we choose lambda and omega carefully, that this term is 0, then you're going to segment your spins into, so that means this ordering is canceled as well as this, and the only thing that survives is the antiferromagnetic interaction between the boundary spins, and that's what you see in this diagram here. So the preferred state after a strong coupling is going to be 2 spins that are up, 2 spins that are down, up, down, and because this still has to be antiferromagnetic. Okay, finally, I'll show you the fully connected Ising model. So unlike the previous 2 models, which were chain models, this Hamiltonian now has a all-to-all interaction. And after this mapping, we again suppress the individual spin splitting, but generate all-to-all ferromagnetic interaction. And then if we now plot the structure factor, what we see this critical lambda that is independent of system size and also temperature. So here's the color coding of what different curves for different length, and dashed lines are for higher temperature and solid lines are for low temperature. And we see is that all of them crosses at the same point. So the intersection between the higher temperature and low temperature, for all of them, all length crosses at the same point, and this indicates genuine phase transition from antiferromagnet to ferromagnet. Okay, so to conclude, this effective method provides a very versatile and analytic treatment that can study even in the non-perturbative regimes of the system bath couplings. And it allows us to quickly examine the dissipation effects to many body systems. And I also mentioned that this method is not restricted to spin half particles or in 1D. It can be you can just use it as is for higher dimensional lattice models and also higher spin models, and also fermionic models, not just spin models. And for the models that I introduced today, it generated only bath-induced ferromagnetic interaction. But by careful choosing of how your system couples to the bath, you can generate more complicated interactions that is not simple ferromagnetic interaction. And I'm currently working on the fermionic chain model that is dissipatively coupled to its bath using this method. And future work includes higher spin models so spins larger than half on a higher dimensional lattice. So that's the future work that I would like to investigate. So this is the preprint information. If you're interested, it has the same title, and it's work done with Nick and Marlon. And if you're interested, this is the archive number. Yeah, thanks.